All right, so on this great day, we're going to do two things, or one thing in multiple ways. So let's look at what we're going to do. We are going to write and interpret something called direct variation. Now that sounds all intellectual and grown up and academic, direct variation, but it turns out it's a lot less complicated than you think. So let's not panic when we see direct variation. Essentially, we're just dealing with fractions. We're multiplying. That's all it really means. So let's actually write that down. Direct variation simply means multiplication. Another way to talk about it is sometimes it's said as proportional. Two things are proportional. So for example, if you had a scale model of the Titanic, it would be proportional to the actual Titanic. If we look at this first one here, it says cross out the ratio that is not equal to the others. Notice that when we attach each one, if I just actually do the division, remember that this vinculum, there's a good name, vinculum, that actually means division, just divide by. 3.5 divided by 1. So we know that this is 3.5. So the same thing, 7 divided by 2 is 3.5. So it gives us the same number over and over again. Same thing here. What about this? 10.5 divided by 3? 3.5. And lastly, 9 divided by 4 gives me 2.25. So in this case, clearly one of them does not match. Which one of them is not like the other? So that's that one there. Now, when we solve proportions, we have habits. So what did you do for number 2? Excellent. So when you do 2 times 9, you simply just get 18, so we can do that. And then the other one equals, good, 3x there. And so when I solve for the value of x, I get 6. We can always test it by putting 6 back into here. And 9/6 reduces to 3/2. Good, so let's look at an alternate way of considering this. Notice that if we just consider, how do I get from a 3 to a 9? I multiply by 3. So that means I have to do that exact same. So this more of is mental math. So, this one works well because it's a multiply by 3. I clearly see that. But over here, this one actually works well too. 3 times 4. So that means I divide by 4 going this way. So yeah, you can do that because proportional is proportional up and down. It's also proportional left and right. So that's a very interesting way of looking at it. Notice that number 3, we can cross multiply. If we did, we get 12x equals 48. The downside of that is you're doing one extra step. Notice this. I could just take and multiply the left side by 3 to get x by itself. So multiply this by 3 to get 16 divided by 4. So then the answer is just x is 4. So notice there's a little bit less work to do if instead of cross multiplying to get this step, you could just skip that by multiplying by the denominator. So in this case, if I just multiply by 2 here to drop the 2's out, multiply by 2 here, I get x equals 10 over 5, or 7, excuse me. Notice I do not have to worry about getting it further. Look, 5 times 2 divided by 7. That's not going to be a whole number, so I'll just leave it like that. That's totally fine. And the last one here, notice I can just multiply by 18 on both sides to get x by itself, and multiply by 18 here, so x is going to give me 4. Where did that come from? That divides, and 2 times 2 is 4. This last one on your review, we're going to come back to quite a bit because this is directly related to direct variation. If a shirt costs $18, how does the total cost relate to the number of shirts you buy? So for example, if I call the total cost C, and the number of shirts I'm calling N, I don't like to say S because my S's look like 5s. In fact, that looks ugly too, so let me clean that puppy up. So I'll do N there. So notice this, my cost is going to be how much times the N? It's just the 18. And notice it will directly affect the number of shirts that I buy will directly affect the cost. If I buy 6, I'm going to pay that much money. If I buy 10, I'm paying $180. If I buy 5, I pay $90. A direct relationship. And so today what we're going to spend our time talking about is direct variation, which is exactly this right here. Notice there's not any additional costs. I'm not adding 12 over here. I'm not making the formula more complicated. It's just simply this. We have two numbers that are related by a multiplication, and that's it. So direct variation, the definition sounds funny, but it's very uncomplex. So here's the definition of direct variation. It is any relationship or any relation between numbers. B/T means between. That can be written in a particular form. And what form is that? Well, if it can be written as this, y equals k times x. Here, let's clarify. My constant of variation is k. So that is my constant of variation. Constant of variation is a funny name because constant means doesn't change, and variation means change. So what this means is that your change stays the same. In other words, add 2, add 2, add 2, add 2, add 2, add 6, add 6. Like with the shirt example above. Every time I buy a new shirt, I add 18, plus 18, plus 18, plus 18. So how much I change stays the same. How much I change stays the same. So that's what the constant of variation is. And by the way, k can be anything. K can be any real number. It can be -1/2. It could be +100. It could be 7.2. It can be decimals, fractions, negatives, positives, it doesn't matter. But as long as it's just one number, not 17 numbers. So we're going to walk through the test for whether or not something varies directly. So let's look here at problem 1. For the table at the right, determine whether y varies directly with x. So what does that mean? All it means is, can I write it like this? Can I write the situation like this? So all I really need is to find some value of k. What's the same number everything gets multiplied by over and over again? So just to show how that works, k is always equal to y divided by x. And hopefully this looks very familiar. Why? Because this is your rise and this is your run. So this should look very much like slope on a y equals mx plus b situation. All right, so we're going to test it to make sure the variation stays the same, that every change changes the same. So how do we calculate that? Well, it's going to be very uncomplicated. All we say is this: k is going to be my -21, and you always just divide by the x there. Take the y, divide it by your x, see what you get. Here I get -7. Yay. Now let me repeat that process. K is equal to, this time I'm going to take the second one, -14, and I'm going to divide it by that second y. And in this case I get, -7. So far so good. I'm not done. Now I'm going to test it one more time because that's all the data I have. Here's my -7, and I'm going to divide it by the 1 there. Oh, lo and behold, since all of these are the same, that's my k. Because they're the same, yes, it varies directly. So how do I answer the question over here? So let me make a little box for my answer. The answer is yes. The answer is yes. It does vary directly. Why? Because k is -7. Every single time to get from the x value, I multiply by -7 to get to y. Here, 2 times -7 is -14. 1 times -7 is -7. So it does work. The last thing it asks me to do is to write what's called a function rule. And the function rule is just substitute in the k. So we just say y equals k times x. So the k just goes in. and that's it. And now what we want to do is be able to check to see if, when we are given an equation, if that equation slash function varies directly. And remember, what does direct variation mean? Direct variation means, can I write it to look exactly like this? Y equals some k times some x. Now, just to give you a heads up, you don't have to use the letter y. You don't have to use the letter x. The most important part is that two letters are only changed by one thing. I'm not multiplying and adding. I'm only multiplying. I'm not squaring. I'm not square rooting. I'm just multiplying, and that's it. Nothing else. So, really, all we have to do is take my original equation and get y by itself. So how do I get y by itself from there? Well, I'm going to subtract 5x from both sides. And in doing so, my first part is this. I get 3y equals negative 5x. Now to get y by itself here, I'm going to divide by 3 and divide by 3. And when I do that, my final result is going to be y equals negative 5/3 times x. So the question is, are these two forms, this here and this here, are they the same? I have y equals some number times x. Y equals some number times x. So the answer here, is it a direct variation? The answer is yes. Why? Because k is negative 5/3. It doesn't matter how complicated looking k is. Like I said, k can be a decimal, a fraction, a positive, a negative, a whole number, or anything in between. And in this case, I can write it in this form, therefore it directly has direct variation. Look at d here, and I get y by itself. I get this function over here. It's a function, but does it vary directly? And the answer is no. Why? Because I'm not only multiplying, I'm adding as well. So there's a k and other stuff. There's a k and other stuff. And this other stuff means it's not varying directly. There's some other factor in there, and we don't want that. We just want just a k and nothing else. The last thing we want to chat about today is talking about an application. Shadows and height vary directly at any given time of day. A 6-foot man casts a shadow that's 4 feet long. So how tall is a flagpole if its shadow is 22 feet? So notice, if I set this up by putting the height of the person on top of a fraction, so the height here is 6 and his shadow is 4. Where am I going to put this 22? Because it's a proportion, meaning it varies directly. So where does the 22 belong? Good, so the 22 is going to go here because, actually let me clarify that. 22 is going to go down here because it is the shadow. So the height, which is unknown, I'll put F for flag. At this point in time, you solve however you would like. You can cross multiply or simply just multiply by 22 to get F by itself. And when you multiply by 22 on this side, you plug all that into a calculator. 6 times 22 divided by 4. And when you do that, F is going to give you 33 feet.